My name's John Tomko, and I'm the Principal Product Development Leader for Capacitor Film here at Peak Nano. We're a supply chain company that's working on providing a solution to power handling, particularly in the form of vastly improved dielectric film in order to replace current polypropylene capacitors. Um, I say all that, I know that's different for most of the fusion folks. Hopefully this kind of ties in later on and we see the importance of this. However, I think the outline for this should be pretty straightforward. Because like I mentioned, we're not a mainstream fusion company like most of the presentations. I thought it'd be useful to get some additional information on Peak Nano and our efforts overall. And this will hopefully naturally segue into a discussion about our core technology and how it's really differentiated from current market options, with particular emphasis on how this fits into the fusion ecosystem. I'll then wrap this up in the form of more discussion on really fitting into that ecosystem further by providing context on our experience with the fusion supply chain in areas where at least I think we can put particular emphasis within the fusion community to improve the supply chain as a whole. And so I'll start with Peak's introduction with this really nice slide from our marketing team. We have this mission statement of delivering nanoscale technology with macro scale benefits in a number of sectors. And really what this means is that we're using a bottom-up approach to material design that allows us to make a new material that fits into pre-existing systems. It's really a drop-in replacement. We aren't trying to make new quantum computers or anything like that when you think of metamaterials. You'll still end up with a complete macro scale capacitor in this case of what I'll be talking about today. It just turns out that this layered metamaterial based design really gives you a lot better net properties than what you might find on the market right now. And so we've been on a fairly decent run with this technology so far. Peak Nano's been producing materials since about 2016, and this is really thanks to a decent amount of capital investment that really allowed us to expedite that timeline from research through development and into production status. And this is really seen in terms of manufacturing capabilities by our 75,000 square feet facilities, which houses about 125 employees. I say that we're always in the process of continuously scaling to manufacture even more material. But we're even more proud to say that we're a fully US based manufacturing company. And so we can really offer a fully domestic supply chain, which is relevant to a lot of the companies here, I imagine. We'll discuss this more in the technology overview, but this is really enabled by a very unique approach in which we create a layered material design. And so by varying the materials within the layers as well as their thicknesses, we can really achieve a wide range of property tuning that you just can't achieve with single materials, blends of materials, or even alloys of materials. And so one of the key benefits of this material tunability that we can enable is that it naturally lends itself towards multiple application spaces very easily. And so we can readily kind of vary this material design to fit a given application as needed. And so the technology I'll show you today is primarily focused around energy applications, particularly film for capacitors, but we're active in a number of other verticals, including packaging, optics, and aerospace, all of which are really enabled by the same design principles I'll be showing you here today. And so I think that's enough marketing for now. What's Peak Nano actually making, and how is this relevant to what we're doing here in the fusion community? Our core technology is really what we call nanoplex film. And so typically when we think of dielectric materials or plastics, they're really composed of a single material system. Maybe if you're really advanced, you might figure out some clever blend of two polymers. But primarily due to manufacturing challenges and technological incompatibilities with a given application, usually find that you can only get so far with these types of approaches. And so what Peak Nano's instead developed is this co-extrusion process shown here that's scaled to production levels already. So this isn't R&D in a university lab anymore. And it really directly enables these multi-layered materials over tens to hundreds of thousands of meters without issue, which is necessary for the scales of manufacturing we're talking about here. And really what this is just a polymeric superlattice. And so what that's doing is effectively taking two polymers, in this case polymer A and B, and alternate stacks of them within a single plastic film. And so we can usually vary the layer numbers anywhere between 10 layers or The most we typically do for manufacturing is 4,092 layers, sandwiched within usually a few microns. And so you're looking at much less than 100 nanometer thicknesses per individual layer. And so what you can imagine is these individual layers enable kind of unique properties relative to their bulk counterparts. And so just to show that this kind of actually works, I just pulled in this nice SEM micrograph of a local region, where you can really see the nice homogeneity of the layers and nice repeatability. And so one example of this, in kind of a more practical sense, is that we can take two resins and make a film with extremely high dielectric constants, up to about 5. These have extremely limited leakage currents, and so this really enables extremely high energy densities relative to if you were just to take a single resin, make it bulk, and the properties you might find with something like polypropylene, which is the current standard, and we'll talk a little bit more about that. And so really this film is now tuned for pulse power applications, but again, the benefit to this layer design is that I can then take two different resins and give you a completely different material system with its own set of properties that is still better than the market standard, just maybe in a different way. And so, for example, here we can take another series of film using two different resins, A's and B's, and make a different material that we call LDF, or low dissipation factor. And so this is really designed to generate significantly less heat. It's really designed for high current applications, and generally outperforms polypropylene in most scenarios where you're really trying to push the limits of how much you can get out of a capacitor. And so more importantly, even if we're ignoring how much heat is generated, let's say it does generate the same amount of heat as polypropylene, this material is designed to have complete stability across the entire operational temperature range. So in most dielectrics, again, using polypropylene as our example, just because it's the standard, you tend to see that as soon as they hit the 100 C mark or so, you have to derate them by 50%. And so you buy a 1 microfarad capacitor, you're now running it at 0.5 microfarads with half the net voltage, which obviously leads to instabilities in your network. And that's not ambient temperature, that's hotspot temperature. And so in most cases, that's an unavoidable process, again, especially when you're talking about high current applications. And so this LDF film really has the benefit that it has constant operational properties, even when these hotspots begin to form. And so you start to gain constant kind of electrical engineering capabilities over its whole lifetime. And so, again, the current industry standard I keep mentioning, polypropylene, specifically what I'm now going to refer to as biaxially-oriented polypropylene, or BOPP, just for simplicity. This is where polypropylene is extruded into these extremely long sheets of plastic. Again, we're talking 40,000 meters length is typically the manufacturing limit for these. And then we take that film and stretch it along both axes. And this stretching process, this biaxial orientation, really is orienting the crystalline domains within the material. And so in doing so, you take a kind of a okay dielectric material like polypropylene, and you give it significantly better dielectric properties. BOPP is pretty much the standard across the world for all energy applications. If you go to the grid, for example, you'll see these large substations, which are running hundreds of BOPP-based capacitors. And the reason for this is mostly because you can intrinsically scale the manufacturing to this as needed, and it gives you the dielectric properties that are pretty okay. And again, just for a sense of the manufacturing scale, we're talking about probably about 1 billion pounds of material a year just in power generation. And so again, this is because you have BOPP's excellent manufacturability. It has pretty good room temperature dielectric properties, but even with all that being said, it still has a slide for now. And those limitations really come in the form when we're comparing our BOPP-based capacitor to peak nanoplex film at a capacitor level. It's a lot to talk about film. It's very different for us to start thinking about how this ends up in our actual device. And so one of the first benefits, again, is this higher operating temperature regime. This essentially means not that you're running it out in the hot desert or in more extreme ambient conditions. It can do that. But even if I have a well-controlled environment, it means I can essentially run the capacitor harder. I can put more net current through it, because it can tolerate the amount of heat generation. So even if the two materials produce the same amount of heat, I end up with this fact that I can just run it harder. Um, in the case of our high dielectric constant material for pulse power, that HDC film I was mentioning, again, really nice parallel to BOPP, just slightly different application space. For pulse power, the energy storage differential between this and polypropylene basically lets you create a significantly smaller net size capacitor housing. When you start talking about costs of capacitor, this starts to matter a lot. Even though you're only, these capacitors, if you look at pulse power applications at Cap Bank, each of these might be 100 pounds of film. It turns out that's actually a small cost of the net capacitor. Most of the cost comes in the form of the housing. And so it starts to matter a lot when I'm buying thousands of these capacitors to power my system. If I can reduce the energy density of each one, the net cost ends up being significantly improved. And so looking at both of these films, just as easy examples, LDF and HDC, really the main advantage is the ability to extend the lifetime under equivalent operating conditions. And so what I mean by this is if we run a BOPP capacitor in the same way that we run these two films, you'll see that these vastly outlast in terms of net lifetime, which means we have less capacitor failures, and we have less capacitor replacements over time. And so your system's running better for longer without needing, manual input. And it also means I'm saving a lot on my capital costs just because I'm not replacing these capacitors at very high frequencies like you do at most high power systems right now. And so, again, a really good example of this is HDC. I'm going to kind of jump back and forth between the two material systems. This is, again, the high dielectric constant. We can kind of see the variety of properties here. As soon as HDC is compared to BOPP, we're getting a factor of 4 volume reduction just because of the improved energy density of this raw film. And so this isn't to say it's the perfect material and that there's no trade-off. You can't put this in every application, just to be very clear. There's a measurable increase in the dissipation factor. Now I say that's not all that matters. You can play some tricks to improve your equivalent series resistance. However, for pulse power applications, when energy storage density really is your primary factor, this becomes an excellent material system compared to BOPP. And again, you can kind of tune the properties between 3.7 and about 5-ish when we're looking at kind of the different product ranges Peak Nano offers. And so again, you have that aspect of tunability for different material systems or needs in the power grid. When we're talking about non-pulsed applications, so again, when we're running at really high frequencies or just DC current applications, you're really talking about heat resistance as being the primary factor of interest. And so I'm intentionally kind of using the term heat resistance very loosely by intention, because it's a really nuanced aspect when we start thinking about it. In some situations, like in power electronics, where we're implementing silicon carbide everywhere, and it's naturally being pushed to 200C operational limits, I'm using heat resistance in that case in the form of whether the film can sustain the same operational temperature as the device itself. Because what happens if you can do that, I remove the need for active cooling. In other words, my capacitor can run at 200C or at very high temperatures. I don't need to implement active cooling. My engineering constraints are simply reduced. But again, there's also this hidden secret on the longevity of the capacitor in terms of heat resistance. And so when the capacitors run at any temperature above room temperature, BOPP gradually gains a derating factor where its capabilities are reduced from room temperature. And then, of course, just from internal heating, the temperature of the capacitor can easily reach 100C in terms of hot spots, which leads to deratings. Now, this derating isn't usually in the form of lower operational voltages, but it also leads to reductions in lifetime. And so, for example, if you run a BOPP capacitor with a 100C hotspot, not 100C ambient, just a hotspot, so again, high current applications, its operational lifetime reduces by orders of magnitude. You'll see most capacitors with a hotspot of 100C, which is easily reached for, again, the current you need for a high HTS magnet, might be 500 hours if you're lucky. And so, again, this becomes a major constraint on what you can get in terms of your net lifetime. And so when we compare that to kind of Peak's product, LDF in particular, this really acts as a drop-in replacement for BOPP. But again, with this idea of really improved thermal stability. where we can sustain temperatures of up to about 135 C. That's ambient temperature. It's not even hot spot. You go quite a bit hotter in terms of hot spot, actually. But what you again find is that you don't have to derate the material, and that its lifetime at high temperature is much closer to its room temperature lifetime. Again, so you gain lifetime and you gain a lack of derating. So just to highlight this a little more clearly, we can consider two capacitors made identically with our LBF film versus traditional BOPP. In the case of BOPP, we can see that the capacitor actually has to be derated by over 30% at 125 C, whereas peak nano's LBF film only loses 5% of its peak performance. And the same is true for that HDC filmed energy storage density or capacitance, which can operate significantly hotter. And so again, this increased cutoff limit on the max operating temperature leads to a direct correlation in the net lifetime of the capacitor, where small hotspots in the device, in the case of LDF, don't lead to detrimental thermal runaway, just because the capacitor can be more tolerant to these conditions. And so this thermal stability is really the direct result of Peak Nano's core technology, which is that production of nano-layered polymeric films. In the case of LDF, the direct drop-in replacement for BOPP, we have much better lifetimes and thermal stabilities. This is actually achieved by taking the same polypropylene you find in every other capacitor, cap-grade polypropylene, and layering it against a high glass transition glassy polymer. And in doing so, the polypropylene effectively becomes stuck within these rigid, well-defined boundary layers. And so this means as temperature or other stresses are applied to the film, like high voltages, the material essentially resists strain and becomes really locked into this well, and gives you constant performance. Because the material is primarily polypropylene, again, it means that the cost is actually very comparable to BOPP, and it really just drops into the same capacitor system with minimal additional effort on the engineering side. And so now I'm saying all of this, I showed that nice SEM micrograph early on, and I'm really used to seeing micrographs of this perfect 100 nanometer region of a super lattice, and everyone calls it the next big thing in their Nature paper, and then you never see it go anywhere, mostly because we all know that if you move a little bit over, you'll start seeing interlayer mixing and things like that. And so, not only has Peak been able to make these scientific advancements in raw materials relevant to this fusion supply chain, but we're actually able to make it at the necessary scale for the fusion supply chain. And so here I'm just showing a batch of film rolls that we produced over the last couple of years, which is easily able to make hundreds of thousands of capacitors. I'm not saying we're replacing every BOPP capacitor today, but we're working very, very diligently to continuously scale up our manufacturing to meet the kind of demands that we're seeing in the market space right now. And so with all this technology, Peak Nano, I think, is really making material that can greatly improve the quality and lifetime of capacitors, particularly, again, for the high current needs that you're seeing in the fusion community right now. And so while our obvious customers are capacitor manufacturers, since we make the raw film, these capacitor manufacturers will then take their capacitor, sell it to someone building a power module or some capacitor bank, and then that system is actually what you'll end up buying as the end user of a fusion company, maybe. So at the end of the day, Peak Nano is pretty far down the supply chain, admittedly. And so from a pure fusion perspective, this is kind of a tricky situation for us. We're obviously highly invested in the progress and outcome of every company because, yes, we believe in fusion as the holy grail of energy generation like everyone else here, but also because if it works, fusion companies will need a lot of capacitors, which means a lot of film sales for us. It's kind of generally beneficial to make sales. And so I say all that, it's also difficult to be invested in the fusion community when we're so far down the supply chain because we know that we can't directly engage with fusion companies to co-develop. And so if I want to know what the current limitations are of a power system or any limitations that you guys are having, it's just intrinsically difficult to join the conversation because there isn't a direct line of communication through that engineering pathway. And so we really have to work upwards through the supply chain, but you see a lot of capacitor manufacturers don't have the knowledge of the fusion supply chain. And so it's hard for them to figure out what are the necessary innovations over time. Now I say this, luckily Peak Nano isn't solely dependent on fusion by being diversified in applications, which I think is core for every supply chain company. and being able to leverage our materials across multiple domain spaces, we can continue to push forward on the main technology and be here really to support fusion in any way necessary. However, I also know that this isn't the case for more niche solutions that may greatly advantage from the fusion supply chain in particular. And so I feel this need to continuously preach the message of trying to close this gap between fusion companies and fusion suppliers, and really encouraging the much needed conversations on current technology gaps and other potential technological solutions that would be able to move fusion faster. And so with that, I think I capped out on my time here. Thank you all, and looking forward to the panel later.